All right, thanks for watching, and today I would like to present a very neat result about polynomials that my friend suggested. So, suppose you have a polynomial f with leading coefficient 1, so that's called a monic polynomial, and integer coefficients. What I want to show you is that if this polynomial has a root that is a fraction, then that root must actually be an integer. So in other words, the only rational roots of this polynomial are the integers, which tells you three things. Either it has no roots, or it has an irrational root, or it has an integer root. And I know this is a special case of the rational roots theorem, but here I just want to do it directly and elegantly. So, how do you show this? Well, suppose you have a rational root, alpha equals p over q is a rational root, a fraction root. And without loss of generality, as usual, assume p and q are relatively prime. Then, of course, the only thing we can do here is just plug in alpha, that root, into your function, into your polynomial, and then what we get is essentially p to the n over q to the n plus a to the n minus 1, p to the n minus 1 over q to the n minus 1 plus dot 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 plus a1 p over q plus a naught equals 0. And then what we can do is just simply multiply both sides by q to the n. So times q to the n and q to the n. And the nice thing is simplifies quite nicely. So what we get is then the following thing. So p to the n plus a n minus 1, p to the n minus 1, q plus dot 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 plus a1 p q to the n minus 1 plus a naught q to the n equals 0. Okay. And then what we want to do, so we want to separate, kind of isolate this p to the n on the right hand side, and what we get is q. Again, the nice thing is here everything has a common factor of q, so q times a to the n minus 1 p to the n minus 1 plus dot 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 plus a1 p q to the n minus 2 plus a naught q to the n minus 1 equals minus p to the n. And here's a nice thing. Well, look at this expression on the left hand side. Well, it has a factor which is q. It's a very cute factor, if you'd like. So q divides the left-hand side, and because those are equal, it also divides the right-hand side. So what we get, q divides minus p to the n, but because, if you want, p and q have no factors in common, well, this kind of implies that q divides p, but then this doesn't make sense because we said p and q have no factors in common. So this contradicts the fact that p and q have no factors in common, are relatively prime. Unless q is 1. So in particular, what we get now is that q equals 1, but what does that tell you about the root? Alpha is p over q, and that is p over 1, and that is p. So the rational root we assume exists is actually just an integer. So in other words, we have shown again that if you have a rational root, then that root must be an integer, which is again a very neat fact about monic polynomials. In fact, you can try this out with the quadratic formula and convince yourself that this is true. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.